Okay, we're going to, again, go around a banked turn, but this time we're going to have friction. So this is going to be a nasty derivation. So we have a cross-section of a banked turn, and we have our car on here. Okay, put them on here, and there we go. And, of course, we're going to have this, which is mg cosine of theta. We're going to have Fn going this way. We're going to have a force coming down this way of mg sine of theta. We're also going to have friction coming down this way, which is mu Fn. Okay? And because we're going to see how fast does the car go around the bank turn before the car flies up off the top. Okay, so that's actually all your forces on there. And it's a little deceiving because if we look at the forces this way, there's a force coming down and a force coming down. That means there's a net force going down this way. Now, what about these two? Well, normally we would think, well, on an inclined plane, that this might be equal to this. But in this case, it's not. This Fn is actually bigger than this. So there's a net force going up. So there's a net force going up, there's a net force going down, which means there's an overall net force going this way. Now, we always knew that because anytime you go around, you go around a circle, you're going to have a net force going in towards the middle. So I'm going to, normally don't draw the net force on the FBD, but I'm going to go ahead and do it on here. I'm going to say there's a net force going this way towards the center of the circle, the track, and of course it's FC. Now I can resolve this one into parallels and perpendiculars to the inclined plane. So there's a force going down this way, okay? And this angle here, theta, would be the same angle as this, okay? And then there's a force going up this way, so this force here would be going perpendicular to the inclined plane. So this one over here would be Fc cosine of theta. And this one over here would be Fc sine of theta. Okay? And what we can do is we can start with two derivations. What is this Fc what is this side here equal to? Well, Fc cosine of theta should be equal to this force and this force. See, these two forces added up are this net force down here. Okay? So that would be mu Fn equals mg sine of theta. That's one equation. Now, the other equation is, what is Fc sine of theta? What's this one coming up? Well, this one should equal, this is a net force, and this one should equal Fn minus mg cosine theta. This is bigger than this, so it gives me some net force going up this way. Okay? I know this is really confusing. So, Fc sine of theta should equal Fn minus mg cosine of theta. Okay, so we're trying to get an equation for everything here. So the thing we don't really know in this is Fn, and Fn is in both. It's over here, and it's right in here. So we're going to solve this one over here for Fn, and then we're going to put it in for this one right here. Okay? I notice I have a mistake here. Fc cosine theta is mu Fn plus, that shouldn't be an equal sign, plus mg sine of theta. This right here is equal to this plus this. Okay. All right, so right here, Fn should equal Fc sine of theta plus mg cosine theta. And we're going to take this Fn right here, and we're going to plug it in for that Fn right there. Okay? And we're going to try to do it on the next page. So this is going to be kind of confusing because I'm going to flip back and forth here. Actually, maybe what I'll do is, okay, that's what I'm going to do. I'm going to erase I'm going to erase this stuff. Just bear with me here. And so I can keep the derivation going here. I think that might be the easiest way. Hopefully you can go back in the video and you can see the drawing and how we got to this point. Okay, good enough. All right, so I'm going to have FC cosine. You know what I'm going to do? I'm going to do some things quickly. So FC is mv squared over r, right? So I'm going to actually put that in right now. So I'm going to do mv squared over r cosine theta equals mu times Fn. What is Fn? Fn is this right here. Okay, so that'd be mv squared over r sine of theta plus mg cosine theta. Okay, that's my Fn. Then plus mg sine of theta. Okay. All right. I'm going to multiply everything by r. Okay. Well, actually, I'm going to distribute this mu here first, I think. Let's just distribute this mu through here first. So I'm going to do mv squared over r cosine theta equals mu mv squared over r sine theta plus mu mg cosine theta plus mg sine of theta. Okay, next thing I'm going to do a whole bunch of things all at once. First of all, I'll just do it right here. I have a mass in every single one of these, so I'm going to cancel the masses all out. I'm going to multiply everything by r. If I do that, the r will cancel here, the r will cancel here. I'll need to put in an r times this side, and I'll have to put in an r right in here also. Okay? And the last thing I'm going to do is I'm going to divide everything by cosine. So if I do that, I'm going to have this over cosine. This cosine will cancel. This cosine will cancel. And I'll have this over a cosine there. That'll actually simplify some things really well. So over here, what do I have left? In the first term, I have v squared. Okay? Equals, what do I have here? I have mu. I have a v squared. Sine over cosine is tangent. Okay? Plus, I have a mu, a g, and an r right there. Okay? And then plus, I have a g, r, and sine over cosine is tangent. Okay? So that simplified it a little bit. I'm going to do some kind of weird things here, though. I'm going to take this term over on the other side. So I'm going to have v squared minus mu v squared tangent theta equals mu gr plus gr tangent theta. Okay? And I'm doing that because I'm trying to solve a velocity equation. So I need to factor out my v squared. So I'm going to take v squared out, and I'd have what? 1 minus mu tangent theta equals, and over here I'm going to take a gr out just for fun, and I have mu plus tangent of theta. Okay? So, I was afraid I was going to run out of this. So what do I have? I have v squared. So if I go to the next page, I'm going to do v squared equals, okay, v squared equals, and I have, I'm going to divide this thing, underneath over here. So I'm going to do v squared equals, and I have a gr, right? V squared equals gr times, and what do I got? On the top over here, I'm going to have mu plus tangent. So I have mu plus tangent of theta over what I have on the other side, 1 minus mu tangent theta. 1 minus mu tangent theta. So the velocity, and this is the maximum velocity. The maximum velocity going around a bank turn with friction would be the square root of GR That's why I like to do that, because we have square root of GER in every single equation we've done, times the square root of mu plus tangent theta over 1 minus mu tangent theta. So this is a nasty, ugly equation for the maximum velocity around it, like a NASCAR track. It's how fast you can go based on mu and the angle, the bank. You got to know about the mu. You got to know about what's the radius of the track. All those three things are important to figure out how fast you can go around the track. Now this equation is interesting. It'll collapse into some other ones we've already done. So for instance, what happens to this whole equation if we're going around a frictionless track, which means mu equals 0? What happens if we're going around a frictionless track? Well, the V, right, is going to equal the square root of GR. And then what do we got over here? We have the square root of mu is 0, so 0 plus tangent theta. So on the top we'd have tangent theta. And on the bottom we'd have 1 minus 0 tangent theta. So we'd have a 1 on the bottom. So the velocity around a frictionless track would be the square root of GER tangent theta. See, we did that one already, see? So this equation here was actually a simplified version of this big equation up here. Let's do another one. What happens if we go around a flat track? So theta equals 0. What happens if we go around theta equals 0, a flat track? Well, again, we have V equals the square root of GER, right, times the square root of, okay, so what's the tangent of 0? Tangent of 0 is actually 0. Okay, so that'd be mu on the top, and on the bottom we have 1 minus 0 would be 1. So what do we got? We have V equals the square root of GER mu, and that was the equation around a flat track. This was the equation over here. This was the equation around a bank turn without friction. This was the equation around a flat track, so angle is equals to 0. So this is the actual equation. This is around a bank turn with friction. And if you don't have friction, it'll collapse to this equation. If you have friction, but you don't have a bank turn, it'll collapse to this equation. So that was a big, long video with a really nasty derivation, which I think was very fun.